In today's lab, we'll be performing an acid-base titration with distilled white vinegar and potassium hydroxide. And we'll be using phenolphthalein as our indicator. The purpose of this lab is to determine the molarity and percent mass and percent by mass of acetic acid in the vinegar through the titration of the solution with the titrant, which would be a solution of potassium hydroxide and distilled water. Or then we will use this experimental data to construct a titration curve. So going on to properties and safety, potassium hydroxide's chemical formula or molecular formula is KOH, and it has a molecular weight of 56.11 grams per mole. It is acutely toxic when swallowed, and it can cause severe skin burns and eye damage. Phenolphthalein has a molecular formula of C20H14O4 and has a molecular weight of 318.3 grams per mole. Moving into the pre-lab questions, the first one being, explain the following terms. So, analyte. An analyte is a solution of unknown concentration, and it's also the solution that will be titrated. So in this case, it's going to be the vinegar solution, and the unknown concentration will be of the acetic acid. Titrant. A titrant is a solution with a known concentration of an acid or base, which is used to titrate an unknown solution. So in this case, it'll be our potassium hydroxide solution. An indicator solution is a weak organic acid, which has a different color as an acid in its acidic form than it does when it forms its conjugate base. So it changes colors after a certain pH. The endpoint is the point during an experimental titration, which best represents the equivalence point. And the equivalence point is a point where the number of moles of the base is stoichiometrically equal to the number of moles of acid. So it's a 1-to-1 ratio. A buffer region is the point during a titration of a weak acid with a strong base, or a strong acid with a weak base, where approximately half of the weak acid or base has been neutralized and has approximately equal amounts of its conjugate base in this solution. And then this forms a buffer which creates a region with where you see the smallest change in pH as volume increases. Your pKa value is a way to quantify the strength of a weak acid. A smaller pKa value, it means it's a stronger acid. Your Ka value is the equilibrium constant for the ionization reaction of the weak acid. And finally, a titration curve is the plot of the pH of a solution during a titration. So it's pH versus volume added of your titrant. For the second one, is there a difference between the equivalence point and the endpoint? So theoretically, there isn't a difference. They're both like where your number of moles of acid are the same as your number of moles of base, stoichiometrically. However, endpoints are used more in the experimental field, so there can be a slight difference in your endpoint and your equivalence point because of that's like where your error comes in. We'll identify the strength of the acid and the base. So acetic acid is a weak acid and potassium hydroxide is a strong base. what is the equilibrium constant, or your Ka, for acetic acid? So that will be 1.8 times 10 to the negative fifth. What is the pH range of your indicator solution, so of your phenolphthalein? It is approximately 8 to 10 pH. On Home Science Tools, which I bought this off of, it says 8.3 to 10, but also 8 to 10. What's the balanced chemical equation? So your balanced chemical equation will be your acetic acid, HC2H3O2, plus your potassium hydroxide plus KOH. Both of those are aqueous or aqueous. And then your products are H2O, water, liquid, plus KC2H3O2, which is also aqueous. Calculate the volume of 0.125 molarity sodium hydroxide needed to neutralize 25 milliliters of hydrochloric acid. So to calculate that, you will first determine the moles of HCl which are in solution. So you multiply your liters of solution, which in this case will be 0.025 liters, times your moles per liter of HCl. So it's 0.1 mole per liter, and you get 0.0025 moles of HCl. Then you take that, and to determine your volume of sodium hydroxide, you take the moles, because it's 1-to-1. It's your 0.0025 moles of sodium hydroxide times, or divided by the molarity of your sodium hydroxide solution. So you end up getting 20 milliliters as your result. Finally, for what is the concentration of a sulfuric acid solution if 50 milliliters of 0.25 m potassium hydroxide is added to neutralize 20 milliliters of your H2SO4, so of your sulfuric acid solution. So to do that, you'd calculate first your moles of potassium hydroxide that you added, but since sulfuric acid is a diprotic acid, so it has two hydrogens, so it's got to do it twice to reach neutralization. So since 50 milliliters total was added, you use 0.25 will give you your concentration. So it's 0.025 liters times 0.25 moles or molarity of KOH, and you get 0.00625 moles of potassium hydroxide. And then to determine molarity, you take the moles of H2SO4 divided by your liters of H2SO4, and you get 0.3125 molarity of your H2SO4. Moving into the research plan. So first, we're going to prepare our titrant and our analyte. So to prepare our KOH solution, we're going to dissolve 1.4 grams of potassium hydroxide, which we have here. Potassium hydroxide, into 250 milliliters of distilled water. Then to prepare our analyte, our vinegar distilled water solution, we're going to add 5 milliliters of our distilled white vinegar and 50 milliliters of distilled water to a beaker, and we're going to add 3 drops of our phenolphthalein indicator solution. We're going to give it a little stir, and then we're going to record the pH. To prepare our burette for the titration, we're going to first rinse it. So we're going to rinse it twice with 2 milliliters of distilled water, and then we're going to rinse it twice with 2 milliliters of our potassium hydroxide solution. After that, we're going to use a funnel, and we're going to fill up our burette to a little bit above the 0.00 milliliter mark on the burette, just in case there's some air bubbles at the bottom. Then we're gonna open up the stopcock and release a little bit of those bubbles right until it gets about to 0. And then that will be our starting point for the titration. And then to do the titration, we're gonna, at the start, begin by slowly adding the titrant in increments of 0.25 milliliters to 0.5 milliliters. I'm probably gonna do 0.25 milliliters on the first one just to see how it goes. And after each increment, after each addition, we're gonna swirl our beaker with the solution, with the vinegar solution, and record the pH. We're gonna start to see like pink flashes in our beaker, and that's gonna be like the acidic change. And so once we start getting near the end point of the titration, we're gonna slow down to adding about 1 or 2 drops of our titrant each time, and like swirl. And when our beaker, our solution has a pale pink color for approximately 30 seconds, that's the end point. And we're gonna you're gonna constantly keep recording the pH during this. And then we're gonna go a little bit more to fill out that titration curve. And then we're gonna repeat that for a total of 3 trials. So let's get to it. So before I get started, I need to first calibrate my pH meter. So I have this calibration solution, and I'm gonna go ahead and calibrate it real quickly to make sure I have it right where it's supposed to be, so I get correct pH meter readings. So I just open up the packet, and then what I'm gonna do is open this up, turn on my pH meter, and then I'm gonna gently insert my pH meter into the calibration solution and let it settle. So we'll begin by preparing our potassium hydroxide solution. So we need to weigh out 1.4 grams of potassium hydroxide, and then dissolve that in 250 milliliters of distilled water. So we're gonna measure out our 1.4 grams. So it's these round flakes. Gloves. I don't want to damage my skin. 1.43 grams. And we're gonna add our water and mix that into solution. So now we'll prepare our analyte. So it's gonna be our 50 milliliters of distilled water and 5 milliliters of our store-bought vinegar. So we'll mix these together, pour them into each other to create our solution with a molarity of acetic acid with an unknown concentration. Then we'll use our indicator solution, and we're going to add 3 drops of our indicator solution to this mixture. One, 2, 3. Put the cap back on that. Let's give it a little swirl. As you can see, I'm just giving it a little swirl. And then that's going to be ready to add our titrant to it. But before we get to that, we got to first rinse out our burette here. So we're going to rinse out our burette by adding first, rinsing it with 2 milliliters of our distilled water. And after that, we're going to do it with our potassium hydroxide solution twice. And then we'll fill it up and begin titrating. So the burette has now been rinsed out. So now we're going to fill it up to the 0 milliliters mark with our potassium hydroxide solution. And then we're going to just open it up just a little bit to get the little bit of bubbles out. And then we'll begin our titration. Okay, so it's now at 0.00 milliliters. So we'll begin our titration by adding going to put our pH meter in there, just so it's getting readings as So we'll start by adding maybe half of a milliliter and then swirling it and reading our So it's now 3.15 pH. Check back in once I've reached the equivalence point. So it's just past the equivalence point, or the end point of our titration, as you can see by this dark fuchsia, is it fuchsia? Here.
Yes.
This dark fuchsia color. So this happened at 45.25 milliliters. So I would say that our actual equivalence point for our titration would be approximately 45.15 milliliters. And the pH between at 45.05 milliliters added of the base to the weak acid, it was 8.4 pH, and then at 45.25 milliliters of base added to the weak acid, the pH was 9.7. So I'm going to keep titrating it just to get that pKb value and like see how the buffer happens at the end of the titration curve, and then I'm gonna go ahead and do my next 2 trials. So after the 3 titrations of the vinegar solution, the analyte, with our potassium hydroxide titrant solution, we're then able to use the information that we collected to calculate the moles of potassium hydroxide solution used, or like the moles of potassium hydroxide used to reach the equivalence point of the of the solution. Then use that to calculate the molarity of the analyte solution, and then use that to determine and then use the moles of the acetic acid to calculate the percent mass of acetic acid in vinegar. So for the first trial, the total volume of the titrant added to reach the equivalence point was 45.15 milliliters. The second trial it was 43.05 milliliters. And for the third trial, it was 46.05 milliliters. Taking that information, we can calculate the moles of potassium hydroxide that were used to reach the neutralization point or the equivalence point by multiplying the volume used in liters by the molarity of the potassium hydroxide solution, which in this case was 0.102 m, which I was able to calculate by using the mass that I used divided by, so taking the mass of potassium hydroxide used in the initial solution, which was 1.43 grams, dividing that by its molar mass, and then getting the moles of potassium hydroxide used, and then dividing that by the liters of solution, or the total volume of the solution that was initially put in, which was 0.25 liter. So then you get 0.102 molarity. So for the first trial, the moles of potassium hydroxide used was 4.603 times 10 to the negative third moles. For the second trial, it was 4.39 times 10 to the negative third moles. For the third trial, it was 4.70 times 10 to the negative third. Using that, we could then calculate the molarity of the analyte solution, which was the solution of the vinegar and the distilled water. Since it's a 1-to-1 ratio of 1-to-1 mole ratio, the mole ratio, that means that the moles of potassium hydroxide is equal to the moles of acetic acid at that point. So you just divide your moles, in this case, by your moles of acetic acid by your liters of solution. So that for this one, it was 50 milliliters of distilled water plus the 5 milliliters of vinegar initially. So it's 0.055 liters. So for the first trial, the molarity of the analyte was 8.37 times 10 to the negative second, or negative 2. For the second trial, it was 7.98 times 10 to the negative 2. And for the third trial, it was 8.54 times 10 to the negative 2. So for the average of all 3 of the trials, it was 8.30 times 10 to the negative 2 molarity. For each trial, you're then able to calculate the percent mass of acetic acid in the vinegar by determining the mass of acetic acid that was in the solution. You just determine that by multiplying the moles, which you previously calculated, by the molar mass to get your mass that's in the solution, and then dividing that by the total mass of the vinegar that you used in the solution. So in this case, the density of the vinegar was said to be 1.00 grams per milliliter. So you just divide your mass of acetic acid in solution by your 5 milliliters, so it's 5 grams, because it's a 1-to-1. And then multiply that by 100 to get your percent mass. So for the first trial, the calculated percent analyte, or percent mass, or mass percent of acetic acid in vinegar, was 5.53%. For the second trial, it was 5.27%. And for the third trial, it was 5.61%. Using this, we can then calculate the percent error based on your theoretical value, because your theoretical value is said to be 5%. So you just subtract your experimental minus your theoretical, and then divide it by your theoretical. So the percent error for the first trial was 10.57%. For the second trial, 5.43%, and for the third trial, 12.83%. There's a lot of places that error could have arisen. It was kind of tedious. But I measured stuff out correctly. So I really don't kind of uncertain about where the differences come from. But there's always the little bit of error from me, I guess. I'm not a perfect person, so it is what it is. But yeah, it was a fun lab. I enjoyed it. 2 more days of chemistry. Let's go. And now, and then I gotta show. So for using the experimental data and your pH readings, you can then form titration curves. So I did that in Excel. I haven't labeled them, so I'm gonna label them and then I'll put them up there. So this was the first page of this lab, which includes the purpose, my references, my properties and safety table, and question 1 of the pre-lab questions. Here are the rest of the pre-lab questions. And here is my research plan on the left side, and then the first page of my experimental on the right side. So this is just all trial 1. This is where I calculated the molarity and the mass, the recorded mass right there. This is the second page of my experimental. This was the rest of trial 1. This is all of trial 2, and then you can see I wrote up at the top the equivalence points. This is trial 3 right here. And then this is the tables at the end for trial 1, 2, and 3 with the different variables. And here are my calculations down at the bottom.